Hi everybody, my name is Or Wertheim and I want to present to you work done by myself and my colleague Dan Swissa under the supervision of our advisor, Professor Brafman. This work is called Plug and Play Task Level Autonomy for Robotics. We will talk about some background and motivation regarding robotics and AI planning, existing systems, the gaps we found, our contribution, an experiment video, an illustrative example, and a summary. First of all, how do companies develop robots today, autonomous robots? So first of all, they implement the basic skills of the robot, like navigation, arm manipulation, object detection, and then they implement a scheduling mechanism to reach a high level goal. And this is not simple. Why? Because robots are physical agents and the actions are not deterministic, so it's hard to plan in advance. And also sensors, they are partial and noisy, making it very hard to manually write such a script. Also, if the environment change, like they have two baskets instead of one in this example that they collect the toys in, or they replace the hardware, the robot arm, then also they need to rewrite this script, which is not simple. Why don't they use AI planning, and then they can just describe a planning problem and they will receive a policy to apply to schedule the different basic skills. They don't use it because it requires significant integration effort, and also there is a gap between robot code and the models used for AI planning. AI planning, it can solve a planning problem, but there are different ways to describe a planning problem, and we think that partially observable Markov decision processes, POMDPs, they are the most appropriate for robotics. Why? So first of all, a robot, as said, it doesn't always know the current state of the world, and also in POMDP, the agent, it maintains a belief state, which is a distribution over possible states. And also in POMDPs, the actions, they are probabilistic, and this corresponds to physical agents, that their actions, they are not deterministic. Once the actions, the agent apply an action in POMDP, then it receives from the environment an observation to update his belief state, and also a reward. This is also something which is good for robotics. Why? Because some planning formalisms, they describe a goal that needs to be reached, but in POMDP you want to maximize a reward function, and sometimes I don't just want to be in a certain place. I want to do it as fast as possible, and I want to minimize risks. So this can be described using rewards. How do we describe a POMDP so an AI planner can solve the problem? We can use an exhaustive description, but this is only good for tiny problems, because even if we have 10 Boolean state variables, then already the state space will be around 1000, and transition function will be around 1 million cells in the transition table. So what do people actually do? They use action description languages. In this example, we see RDDL, which is used for POMDP. In this example, you see the wildfire domain. In this domain, you have 9 cells. Each cell can be burning or not, and it can have fuel or not, and it can be a target or not, and the agent can put out a fire, and it wants to prevent the fire from spreading to target cells. It can spread to neighboring cells. In RDDL, we can see that even though this problem it's not tiny, you can compactly describe the transition function as we see here. And RDDL is very expressive. You can use if-else conditions, and also you can sample from Bernoulli distribution and other common distributions to describe probabilistic changes in the world. So we can see that we can compactly describe domains using action description languages. We have a claim. We are saying that current ADLs, they are not expressive enough. I will give two examples of things you can describe with RDDL, which, as I said, it's very expressive when you're relating to other action description languages. But these two examples, it shows something deeper. I think that action description languages, they are not mature enough if you're comparing them to probabilistic programming languages. The first example is if I want to describe that when I'm applying an action, then I constantly sample a random cell until I find a cell that meets a certain condition, and then I will say that this cell is bounding and I will stop sampling. This cannot be described using RDDL. Why? Because they don't have while loops. Another example is that in here I say that we see that the fire, it can spread to neighboring cells, but the list of cells is static. It's something exhaustively described in RDDL. But what if in my domain the neighboring of a cell, it can be dynamic? So this cell can change that it has 1 as a neighbor, and maybe it has 3 neighbors in these places that the fire can spread. So this cannot be described using RDDL. And another thing is that we have an abstraction gap, that when I want to activate the put out action, when I want to activate a code of a skill, of a robot skill, then I will need to translate this high level description of an action to something that activates a robot skill. So we have a gap, low level code and planning model. What do we think is needed? We saw that probabilistic programming language can compactly describe complex probabilistic domains, and we think that an action description language which is powered by a general purpose programming language is something which is required to describe real world problems. C++ is used by engineers to solve real world problem, so it can describe complex problems. It's very expressive. It's widely used in robotics. It has a large set of implemented code for constructing and manipulating data structures. And so this is what we think is needed, an action description language like RDDL, but powered and have the expressive power of C++. What are the available systems when we want to integrate robotic and AI planning? So first of all, we have ROSPlan. ROSPlan it's the first system that was published, and it supports PDDL. PDDL is a planning formalism that can describe only deterministic actions. So if something unexpected happened, like the robot didn't act as expected, then you need to perform replanning, and this can cause repetitive behavior. If it happened over and over, then you will something which is unexpected happen, then you will perform replanning. And also if there is noisy sensing, then also it can cause repetitive replanning and repetitive behavior. They also support RDDL, but they support it in a limited way without supporting partial observability or noisy sensing. So only if you can sense the world, then you can describe probabilistic actions. It requires significant integration effort. We experimented with it. So we think it's a good system, but it has its drawbacks. There is also the CLIP executive and the skill-based architecture. Both have their unique advantages, but they don't support probabilistic planning, probabilistic actions, only deterministic actions. So the gaps we found that current action description languages, they are not expressive enough for real-world problems. There is an abstraction gap between planning problems and low-level code. Available system, they require the user to write code that stitches between the robot skills and the system. So this is a significant integration effort. Current systems, they use planning models. They don't support partial or noisy sensing, and most of them don't even support probabilistic actions. And we also think that a solution shouldn't be tightly bound to any specific robotic system like ROS-Plan, which is tightly bound to ROS. What is our contribution? We introduce the AOS. It's a complete methodology and tools to automatically bridge the gap between basic skill and AI planning. The AOS is a plug-and-play solution. What does it mean? It means that the user should only document his basic skills and the goal of the robot, and the system will perform all the rest. It will auto-generate the code that stitches the skills to the system. It will activate the skills when needed. It only needs the documented code. The basic skills, they will each be described using two documentation. One, it's a high-level documentation that describes the behavior of the skill. This will be a C++ action description language we introduced. It's called JSDL. And another documentation is the abstraction mapping. This AM file, it will instruct how to activate the code of the basic skill, and also how to calculate the outcome of the skill and to translate to something that the AI planner can reason with. So this will bridge the abstraction gap. And there will be an environment file to describe the possible state variables and the robot objectives. Let's overview on the architecture of the system. Let's start bottom up. The functional layer, this is the robot framework itself. We have the middleware. This middleware, once a basic skill was scheduled for execution, it can activate the actual code, and this component is auto-generated based on the AM documentation. It can also listen to public data changes inside the robot framework, and it receives the response from the skill code. Then it calculates an outcome that the planning engine can reason with. The planning engine is where the AI planning algorithm is running. Its role is to schedule the basic skills for execution. We use a sampling-based algorithm, and this in this sampling-based algorithm, it has its advantages, and the sampling rate is significant to get good policies. And we experiment between two approaches. One is to use a generic code that can handle that can receive a description of different domains and sample from them, and the other one is that we auto-generate specific code that describe a specific domain, and from it we can sample trajectories of the domain. And we saw that the auto-generated code is 40 times faster than generic code, and we used RDDLSim. It's open source code that was used for the international probabilistic planning competition. So once the user interacts using it sends a request to the web API of the system to integrate his code, then the planning engine and the middleware are auto-generated and the system it starts to operate the robot. Let's look at an experiment. Okay, so in here we see our Panda robot. It's a robot arm. We have in the lab, we implemented two basic skills. One is to write a circle inside the tic-tac-toe board, and the other one is to detect when the board state changes. So we implemented these two basic skills, and we documented inside the environment what are the desired states and what are the undesired states, and we see that the robot is acting in a sensible way to win the game. In this experiment, the actions themselves, they are deterministic, but we just want to see how easy it is to use the system. It took us 1 day to implement the skill and another one to document and experiment with the robot. This is the armadillo robot in the second experiment, and what we implemented here are a few basic skills, but here the basic skills, they are not deterministic. The pick action, it can miss the can, it can drop the can, or it can pick the can, and we describe all of this using our documentation and the other skills, and we are seeing that we can expressly describe complex behaviors and to receive sensible behavior from the robot. Let's look at an illustrative example just to get the look and feel and to see how expressive our system is and flexible. In this example, we have a robot with a single navigation skill. It needs to navigate as fast as possible to 3 known locations. Now the navigation can fail. It has a 10% chance of failing, and 80% of the times it fails, it reports failure, and otherwise it reports success, so it has noisy sensing. Let's start bottom up. This is our abstraction mapping documentation to bridge between low-level code and the system. So in here we describe how to activate the basic skill and what are the possible outcomes of the skill, and we can describe local variables based on public information published in the robot framework, or parameters sent by the planning engine, or also the response from the skill code. And this is how we bridge the gap. The system knows how to activate the system, how to activate the basic skill, and also how to send a proper response to the AI planner. This is the environment file. In here we are saying that our goal is to visit the 3 locations. You can describe special types and to declare them, to describe the initial belief state, and more. And this is the JSDL. This is how we describe the high-level behavior of the navigation skill, and we can see it can receive a parameter and to describe the robot discrete location. After executing the action, we have a 10% chance of failing, and we can describe the model, the observation model, which in this case is noisy, because when we fail, only in 80% of the time we are saying it failed, otherwise it was successful. And also we can describe the cost of applying the function. This is the reward model. We can easily describe the distance traveled and more. So let's summarize our contribution. We present the AOS. It's a plug-and-play solution that bridges between basic robot skills and AI planning. We introduced the JSDL, which is an ADL powered by C++, and our abstraction mapping that bridges between planning domains and low-level code. For future work, we plan to perform a user study on the AOS to support multi-agents, and we have a work in process on anomaly detection. Also, we want to improve the documentation given by the user to improve this model we are building based on it, based on the robot experience. So we will learn more accurate documentation, and we will receive better behavior from the robot. Thank you very much.